Right now, Voyager is still sending data back to Earth from the edge of the heliosphere about 120 astronomical units out. That is roughly 120 times the distance from Earth to the Sun. And the moment it crossed that boundary, the radiation environment changed fast. Solar wind particles dropped sharply, galactic cosmic rays surged. But here's the paradox. The magnetic field direction barely changed. In 2012 and again in 2018, Voyager 1 and Voyager 2 crossed that edge from two different directions. Both saw the same thing. So what is this boundary really? A hard wall or a blurry interaction zone between the Sun and the Milky Way? Stay to the end, because there is one detail that took NASA a long time to confirm. Voyager entered interstellar space, yet the magnetic field direction stayed almost the same. That was the opposite of what many models predicted. In this video, you are going to explore the solar system in 3 layers. Layer 1, what Voyager measured at the exact moment it crossed the heliopause, the signature of a radiation environment switch, is densities, the that ER2. Why that boundary is not a thin line. It has a compressed layer and a transition region. It is a physical structure we can measure. Layer 3, the most important one, what all of this says about how the Sun interacts with the galaxy, where the true boundary of the heliosphere sits and whether it breathes over time. Most people think the solar system ends at Neptune or Pluto. It does not. What surrounds us is a gigantic plasma bubble called the heliosphere. It is inflated by the solar wind, a non-stop stream of charged particles flowing outward from the Sun. It is like a breath that never ends. But outside that bubble is not empty space. Outside is the interstellar medium. Extremely thin gas, dust, the Milky Way's magnetic field, and especially cosmic rays. When the solar wind pushes outward, it collides with that interstellar environment. Particle pressure wrestles with magnetic pressure. That battle builds 3 boundary layers. First, the termination shock, where the solar wind suddenly slows down. Second, the heliosheath, where particles pile up, heat up, and become more turbulent. Third, the heliopause, the boundary where the Sun's direct influence effectively ends. These layers matter because they determine how strong the solar system's radiation shield really is. Before Voyager, most of this was simulation. No one had ever measured this edge directly, until Voyager touched it and sent back real data. Voyager 1 and Voyager 2 launched in 1977. Their hardware is almost unbelievable by modern standards. Memory measured in kilobytes. Transmit power closer to a refrigerator light bulb than a modern antenna. But they had something many spacecraft still rely on for deep space: RTGs. Nuclear power systems that can run for decades. And most importantly, the 2 spacecraft went out in different directions through the heliosphere. The same edge, but 2 angles, like watching a storm through 2 different windows. When Voyager 1 crossed the heliopause in 2012, the data flipped in a way that was impossible to miss. Solar wind particles plunged. Galactic cosmic rays spiked. Think of it like this. Inside the heliosphere, the particle environment is dominated by the Sun. Cross the heliopause and you step into an environment dominated by the galaxy. What shocked scientists was how narrow the boundary appeared to be. The conditions changed almost immediately. That means the heliopause is not just a concept on paper, it is a physical boundary, a real doorway. But it is not only about particles, it also shows the heliosphere behaves like a radiation filter. It knocks down some fraction of cosmic rays before they reach deeper into the solar system. And that is why this matters for humanity's future. Once you leave Earth, radiation is not a theory. It is a survival problem. Galactic cosmic rays are not harmless. They are extremely high-energy particles born from supernovae and other violent events across the Milky Way. The heliosphere bends their paths and reduces their overall flux. The heliopause is where you can see that shield switch on and off most clearly. Voyager showed the filter is sharper than many predictions. Just past the boundary, cosmic rays rose rapidly, while solar wind particles almost vanished. If you want to go to the Moon, Mars, or beyond, this is the problem you cannot dodge. Now we reach the part that confused scientists the most. Before Voyager, many models expected this. The Sun's magnetic field and the interstellar magnetic field would meet at the heliopause with a clear tilt between them. That tilt should create strong twisting and turbulence. Voyager measured something closer to the opposite. The magnetic field direction on both sides of the boundary was nearly aligned. It was like 2 oceans meeting, but the magnetic currents ran parallel instead of colliding head-on. In simple terms, you step from region A into region B, and your imaginary compass barely moves. So the question started. Is magnetic reconnection happening here in a more subtle way than expected? Or is the heliopause not a rigid wall at all, but a transition zone where field lines are bent, folded, and rebuilt? This is also why NASA was extremely cautious when announcing Voyager has entered interstellar space. One signal that should have changed dramatically did not. And when Voyager 2 crossed from another direction in 2018, the picture sharpened. The old models were missing a key mechanism. Stay with me here, because if you understand this, you will see why the edge of the solar system does not behave like a line on a map. It behaves more like weather than a border. When the solar wind hits the interstellar medium, it does not shut off. It slows down, it compresses, it piles up. Right near the heliopause, a contact region forms where particle pressure and magnetic pressure keep tugging against each other. Voyager 2 measured a crucial detail. The plasma just outside the boundary was hotter than expected, on the order of tens of thousands of Kelvin. But it is so thin, it is essentially a near vacuum. It is not hot like fire. It is more like an extremely sparse fog. Each particle carries a lot of energy, but there are not enough particles to heat matter the way we normally imagine. This is where simulations struggle the most. The heliosphere is not a smooth sphere. Its boundary is distorted, rippling, folded, and changing with time. It is shaped by interstellar pressure and also by pulses of solar wind that propagate outward like waves. So Voyager 1 and Voyager 2, leaving in different directions, encountered two exits with different properties, but all of this only matters as long as Voyager can still talk. And here's the twist. In November 2023, Voyager 1 started sending back a signal that could not be decoded, not because it ran into something out there, but because part of its flight data subsystem memory began to fail, likely due to decades of accumulated high-energy radiation. Each command from Earth takes about 22 hours to reach the spacecraft. NASA had to reorganize the code to avoid the damaged memory. It was like repairing an operating system from tens of billions of kilometers away, and then it worked. On April 22nd, 2024, Voyager 1 resumed sending engineering data. On May 22nd, 2024, it began restoring science data. On June 13th, 2024, the surviving instruments returned to a normal measurement cadence. The most valuable part is simple. Voyager is still speaking. For the first time, humanity does not have to guess where the edge of our heliosphere is. We have real measurements. Voyager forces us to redefine what we mean by the edge of the solar system. That edge is not a planet, not Pluto, not a label on a map. It is an environmental boundary, a plasma and magnetic frontier where the sun's direct influence weakens and the galaxy's interstellar environment begins to dominate. But there is a deeper layer. The sun does not stand still. Over millions of years, it moves through regions of interstellar space with different gas density and magnetic conditions. If the sun enters a denser interstellar region, the heliosphere could shrink. If that happens, more high-energy radiation could penetrate deeper into the solar system. There's also a common confusion. Voyager has entered interstellar space, but the solar system, in the sense of matter still bound by the sun's gravity, extends much farther out to the Oort cloud. In other words, our edge is not fixed. It can expand or contract depending on the Milky Way's local conditions. And Voyager is the first mission that lets us measure that boundary directly, not just simulate it. One day, Voyager will go silent. But before it does, it has already told us something that changes how we see space. The space between stars is not empty. It is an environment. It has structure, magnetic fields, pressure, and radiation. And the heliopause is where those two worlds collide. Now it is your turn. If you could name this boundary, what would you call it? Write one sentence. I would call it, if you found this video useful, hit like and subscribe so you do not miss the next one. Thanks for watching to the end. I will see you in the next video.